Hello and welcome to a deep dive into the AWS Nitro System. My name is Ali Saidi. I'm a senior principal engineer in AWS, and today I'm going to talk to you about Nitro and why we've done things in a certain way and what benefits you can get from that. So far in AWS, we've built silicon and chips in multiple different areas, spanning IA, core compute, and machine learning. The first place we invested in silicon was the Nitro System, where we moved functionality from a traditional hypervisor to a purpose-built chip. This started back in 2013, and then working with a startup called Annapurna Labs that AWS would later acquire, we continued to do that. Most of this talk's about the Nitro System. I'm going to dive into it a lot. But before I do, I want to give you just a little flavor of the other places that we've invested in silicon. The first is with Graviton, where we built a host CPU that delivers the best price performance in AWS for a wide range of cloud workloads. And we have customers today like Epic Games, Stripe, Pinterest, Datadog, and even SAP who are running workloads on Graviton today. Some of these customers are running the majority of their compute on Graviton. The third place that we've invested in custom silicon is with our machine learning accelerators, Inferentia and Trainium, that are built from the ground up to deliver the best price performance for machine learning, inference, and training workloads. And here we have customers like Databricks using them. So why do we build our own chips? And the answer here is simple. We build our own chips when it leads to direct customer value. And by building our own chips, we get to do some things differently. The first is we get to specialize them for our use cases and the use cases in AWS. Specialization lets us tailor our designs for operating in the AWS environment and focusing on the specific needs we have. You might say, well, of course, why wouldn't any piece of silicon be tailored to a specific market? And really, when you're building a chip and you're spending the time building a chip, typically you want that chip to apply to as many markets as possible so you can amortize the cost of doing so. But that means you've got to add an amalgamation of features to it. With us, we focus on just our use cases, which lets us optimize performance and power efficiency. I'll show you today how we tailor the AWS Nitro System to AWS's infrastructure to improve both performance and security in our servers. The second is speed. We get better speed of execution by owning the end-to-end development process, going from concept all the way through to deploying that system into our data centers and giving it to you. That just lets us bring technology to customers faster by owning that process. We get to shrink the time from concept to deployment. The third is innovation. By building our own chips, we get to innovate more and thus create more value. And what I mean here is when you've got the teams building the silicon, the motherboard, the server, the firmware, the hypervisor, the racks, the infrastructure, all under one roof, you can innovate across typical silos to build an optimal solution and do optimizations that weren't possible if you were looking at just one of those components. And lastly, security. Nitro provides us a way to enhance the security of our servers through hardware roots of trust, verification of firmware on the server, and limiting interactions with the host through a narrow set of authenticated and audible APIs. Nitro is really a fundamental rethink about how virtualization in the cloud should be done. At its lowest level, the Nitro system is Nitro cards that offer networking, storage, and security functionality. In the host processor, we run our Nitro hypervisor, and on top of that, your VMs and your applications. I'll talk to you today about how this separation provides better security and has allowed us to innovate and bring you new features. But before I do that, let me talk a bit about how we got here. And it all started with a simple question. After building EC2 for almost a decade, if we applied those learnings, what would we change in the systems that we had? And there were a lot of suggestions here. There were performance suggestions like improving throughput, simplifying the hypervisor, reducing latency and jitter, and having bare metal performance. On the other side, there were security features like transparent encryption, a hardware root of trust, removing operator access, and a narrow set of audible APIs. And Nitro gave us an opportunity to implement all of these. Nitro is a combination of hardware and software, the chips that we're building in AWS and the firmware that runs on them. We've got 5 generations of chips now. We introduced Nitro back in 2017 with a C5 instance, but really this all started back in 2013 with the C3 instance when we debuted enhanced networking. And we started moving some of the functionality that was traditionally in the hypervisor onto a special purpose chip. This provided higher performance networking, lower latency, and improved CPU utilization of the host. Over time, we've expanded this with newer Nitro cards and to other I/O. So not just networking, but also storage. And ultimately, we built a hypervisor where we got to remove a bunch of functionality. And since 2017, all the EC2 instances we've launched, and there have been a lot of them, have been using the Nitro system. So here's what one of our systems looked like before Nitro. We have the customer instances. These are these orange boxes here. And they're running on top of the hypervisor called Zen. Now Zen's great, but it also did a lot. It did memory management and CPU scheduling, but it also did device emulation, limiters, security group enforcement, and quite a bit more. It even had a full-blown Linux user space and this privileged DOM0. And all of this functionality used resources on the host CPU. So we started offloading them onto special purpose devices. And the first place we did that was in networking. So let's dive into that. So we have a family of Nitro cards that do different things. Some do networking, some do storage, some do both. And with a Nitro card for VPC, we offloaded the I/O functionality of the Nitro card. If you took one of these cards, on one side you have something that looks an awful lot like a PCIe connector. It's not quite, but it looks like it. And it has a bunch of virtual functions that each provide an ENA device that's connected to your instance. And on the other side, we have a network adapter. And what it did was it offloaded the VPC data plane. So things like ENI attachment, security groups, flow logs, routing, DNS, DHCP, and a few more. All of that used to run on our hypervisor, and we moved it to dedicated hardware. The newer versions of our Nitro cards support transparently encrypting network traffic with 256-bit AES without any performance change. So if you enable encryption in your VPCs, you just get that transparently. And what you see in your instance here is the ENA device, the Elastic Network Adapter. One of the cool things about ENA is if you look at how it's evolved, it started with offering 10 gigabits of networking, and then 25, and then 100, and now 200. All with the same device model and the same drivers. You can take an AMI that's working on an old ENA device and run it on a new one, and you get a massive performance increase. And it's pretty unique actually to see an order of magnitude increase in performance with the same device and driver. The other thing that we got with our Nitro cards for VPC networking was the Elastic Fabric Adapter. EFA is a network that's geared to HPC and machine learning workloads. These are special. They need both low latency and high bandwidth. Typically, you have workloads that need high bandwidth and latency is not as important, or they need low latency, but they don't use a lot of bandwidth. HPC and machine learning workloads are different. They need both. And so with EFA, we actually use another AWS developed technology called Scalable Reliable Datagram, or SRD. SRD achieves this by load balancing traffic across many paths through our network to reduce congestion and avoid hotspots. Let me tell you a little bit about how SRD works. Traditional networking protocols take a single path to the network. So if you start at the server on the left, you pick one path through the network to get to the server on the right. Now, they're slow to react to congestion and even slower to react to any failures. But with a network that looks like this, it's a CLOS network. There are many paths between those points. And if you can use more of them, that's great. You can detect congestion, you can route around it, you can use a lot more bandwidth, at the same time. And you can do that in data center scale times, not internet scale times. And that's what we do with SRD in our Nitro cards. It provides a foundation for using many of these paths simultaneously, allowing us to distribute bandwidth across them all, detect congestion quickly, shift traffic to uncongested paths, and avoid any paths that have link issues, which ultimately reduces tail latency and increases bandwidth. Tail latency is particularly important in these kinds of distributed applications because in a lot of cases, they're bulk synchronous. They do some computation, they do some networking, and then after all the networking messages get exchanged, they can start doing computation again. With a system like that, the median latency or the average latency isn't that important. What's the most important is the P100 latency, the tail latency. So let's look at how SRD has worked. Here I'm showing a graph of cores on the x-axis and scaling on the y-axis. And ideally, you'd be on that red line. That's perfect scaling. Without EFA, that's the purple line. So you can see we start scaling, we get up to about 400 cores, and then it flattens out and even starts going negative. With EFA, we get to scale close to linearly for a lot longer. The first version of EFA supported up to 100 gigabits of networking, the second up to 200 gigabits of networking, and 30% lower latency. Another place we've used SRD is generic networking. But before I get there, let me talk to you a bit more about how TCP reacts to a network. TCP expects in-order packet delivery. So traditionally, flows are hashed to a single path of the network, and they take that path, and they arrive in order. And with traditional routing, that flow, a single connection, flows like that. Now, sometimes a large flow ends up hashing on the same path as a different one, and even in an over-provisioned network, there's congestion. And this can result in switches struggling to cope with the load. They ultimately drop packets, like you see here in the yellow. Now, that makes TCP back off, it reduces bandwidth, and your traffic keeps flowing. Other times, you have a situation like here in red, where there's a problem with a link. TCP congestion control is okay with dealing with some packet loss, but when you lose the link, what happens is TCP doesn't respond well at all. You have to wait for the connection to time out, you reestablish a new connection, and then you carry on. So you can think, well, you've got multiple paths to your network, why can't you just use them all? Well, TCP has this expectation of in-order delivery. If I sent traffic down multiple paths, packets would arrive out of order. And then the congestion control algorithm would say, something's wrong with the network, let me reduce bandwidth. With ENA Express, what we're doing is we're offloading that to our Nitro cards. And while TCP doesn't handle those out-of-order segments well, we take TCP, and then the Nitro card uses SRD to fan it out across the network, reassemble the packets in order at the other end, and provide them to your application. So you get the benefits of SRD and the benefits of using multiple paths without making any changes to your application. And the benefits here can be pretty extreme, especially for workloads like file systems, in-memory databases, and some media encoding. We see a 5x increase in single flow bandwidth from 5 to 25 gigabits. And we've shown up to an 85% improvement in in-cast benchmarking under high load. So like I said, it's a simple thing to configure. You just configure ENA Express on your ENA device. It's an API or a toggle in the console. And in the same AZ, it's transparent to TCP and UDP, and you get much higher performance. The performance that we've seen increase in networking here has been pretty remarkable. When EC2 started, 1 gigabit networks were common, and had been that way for almost a decade. Today, there's been a huge shift from 10 gigabit to 25 gigabit to 50, 100, 200, and now we have instances with multiple terabits. The increase in network bandwidth and performance here has been really astounding over the years. The next place that we we applied the Nitro system was in storage. So let's take a look at that. Along with the ENA devices I mentioned that our Nitro cards provide, they also provide a set of NVMe devices. NVMe is a great standard protocol with standardized drivers, and the Nitro card exposes NVMe interfaces on one side and converts those to our EBS data plane on the other. Just like with networking, if you enable encryption in your EBS volumes, that happens transparently on the Nitro card without any performance delta. And so you don't have to make a trade-off between encryption or not there. And just like I mentioned with the networking, here too we also use SRD. When you make a storage request, we send that request down multiple flows through our network to our storage servers to get better tail latencies for your storage workloads. And just like with networking, if you can see a large increase in performance. If you go back a decade, we offered 2 gigabits of EBS bandwidth. Today, we offer up to 100 gigabits and up to 400,000 IOPS. Now, EBS is great. It's the right answer for most of our customers. You get better durability and snapshots, but some workloads need local storage. So that's another place where we've invested with a Nitro system. Now, before I get into how this works, I need to give you some background about how flash works and how an SSD works. There are really 2 important components on an SSD. The first is the NAND. That's where the bits get stored. But NAND's a little peculiar. If you want to just change a byte or a bit even, you can't. You have to erase a whole block to be able to write it in NAND, and blocks are usually about megabytes. So to deal with that, you have something called a flash translation layer. This maps logical addresses to physical addresses, performs the garbage collection, because if you want to change a file and a byte in a file, you actually have to copy the whole file, make that change, and then free the old one. But again, in like megabyte chunks. And the FTL also manages wear leveling. Flash has a certain lifetime, you can only write it a certain number of times, and so you want to spread writes across all the flash devices. And if you think about this, ultimately you end up with something that looks a lot like write logging in a database. You write a bunch of data, and then you kind of clean up the garbage afterwards. And just like databases, every SSD vendor has their own FTL implementation. And they all behave a little bit differently, even though they all have the same external NVMe API. In the average case, they all do a good job, but in our experience, they all have odd and unpredictable behavior sometimes. For example, garbage collection kicks in at just the wrong time and suddenly causes requests to stall. And these sorts of behaviors make it difficult to engineer really consistent performance and run certain workloads, like databases, with consistent latency. So how can we get the performance here that we need? Well, we integrated the FTL onto our Nitro cards. And with that, we get up to 60% lower latencies, improved reliability, and again, encryption with an ephemeral key here. Just yesterday, we announced the I8G instance with our 3rd generation of ASSDs, with up to 65% higher real-time storage performance and 50% lower latency variability compared to our i4G instances from a couple of years ago. So with this, we've moved away from the hypervisor and the host CPU onto dedicated hardware, the networking, the storage functionality. And you can see DOM0, that privileged domain in Xen, is now significantly offloaded. And most of its functions are handled by the Nitro system. So after offloading all of that I/O, we can go back and revisit what does the hypervisor really need to do for us. And this led us to a lightweight hypervisor with a lot of those functionalities we just talked about removed. It just does memory and CPU allocation, and then it gets out of the way. There's no SSH, there's no systemd, there's no networking stack there. It's really small, and small here is great. Small means it's not using many resources, and if you're not asking to do something, it's not getting in the way. And with this, we get bare metal-like performance. If you compare a metal instance to a virtualized instance of the same size, you normally cannot see any performance difference. It's practically bare metal. Additionally, we've added the Nitro security chip to our servers. So motherboards have components to measure fan speed and temperatures, and we want to be able to update all of those as well and make sure that they're running the latest versions of firmware. And that's what the Nitro security chip gives us. It gives us a way to measure the contents of flash devices on the motherboard, confirm they're matching our expectations, and to update them out of band. So with this, we can move the management and security and monitoring over to the Nitro cards, and then switch to using our Nitro hypervisor. And we talked about performance and security, but there's one more aspect of the Nitro system that I want to share with you. It's a modular design. We've got many cards, we can put them in different servers, we can build different configurations. And if you go and look back, it took us 11 years to go from 1 instance to 70 instances. And then with the Nitro system, we've gone from 70 to around 850 today in 7 years. So this is a massive increase in the number of instances that we have to provide you with all the flexibility for different storage configurations, networking configurations, accelerators that we just couldn't have done before in the way that, before Nitro. Okay, so we talked about networking, we talked about storage. Let's spend a little more time on security. Security in AWS is a shared responsibility model. AWS is responsible for the security of the cloud. We operate, manage, and control the components from the host software, the virtualization layer, down to the physical security of the facilities that we're operating the service. The customer is responsible for the security in the cloud, which for a service like EC2 means performing necessary security configurations, like what your security groups are set up, keeping your OS up to date, and how your VPC is configured. In the past couple of years, there's been a lot of interest in computing, but also some confusion there. We look at it as protecting customer code and customer data. And the first question is typically, well, who are you protecting this from? Usually it's code and data from other customers and from the cloud provider. This is called Dimension 1. And Nitro builds mechanisms that protect customer code and data from outside access. It's fundamental to the design decisions we've made with Nitro. Let's recap some of those. So Nitro provides physical separation from where your code is running on the host CPU to where our code is running, which is primarily on our Nitro cards. When the system boots up, our Nitro cards with the Nitro security chip can measure and verify the contents of firmware in the servers, and only after that unlock the storage of the server and actually run your instances. We're able to live update all the software on the hypervisor without downtime, or on the system without downtime. And this software is developed by a globally distributed set of teams, subject to multi-party code review and extensive testing, cryptographically signed by an automated build pipeline, and deployed by the EC2 deployment system, which defines the deployment policy and the schedule, and monitored during deployment and triggering rollbacks if anything anomalies are noticed. Most importantly, there's no remote access to the hypervisor. There's no SSH server. There's only an API that's encrypted, authenticated, authorized, and logged. And none of those APIs support a way to access customer content. The second dimension is dividing customer workloads into a more and less trusted component. This separation can limit your operator access and also bugs in your application from exposing data. One common case here is to put a private signing key inside the enclave. So if there's a bug in the application, those keys can't be accessed. So if you have all the protections of a regular Nitro instance, what did the enclaves give you? Well, they're another instance where the parent is donating some CPUs and some memory. And then the Nitro hypervisor is creating a new VM. And that VM doesn't have any persistent storage. You can't SSH into it. It's highly constrained, and it only has a small straw back to the parent. The parent can't access the processes or applications inside of it, but what you do is you get an attestation report of that enclave. And inside the enclave is a private key, and the attestation report has a public key. And so you can use that to encrypt data that goes into the enclave, and then the parent instance has no access to it. And with that, you can secure your most sensitive data in that enclave, like signing keys or PII. We've added a few other features to our Nitro instances recently. One is UEFI Secure Boot. So AMIs actually provide an immutable way to boot an instance. But customers have had Secure Boot on-prem and have asked if they can use it in AWS. And so with Secure Boot, we measure the bootloader and the OS and compare those measurements to UEFI variables. And only if they pass does the system boot. This provides some additional defense in depth for any kind of threat that would persist across reboots, since the instance will only boot if its software is signed by the keys that are in the UEFI variables. We've also added support for Trusted Platform Modules, or TPMs. We have a standard TPM 2.0 interface that's exposed to the instance. As the instance boots, it extends measurements into the TPM. The measurements have the platform identity and can be used to generate cryptographic data, and that data can then be used to unlock LUKS or BitLocker or custom applications that you create. I've just talked about security in the Nitro system for a few minutes, but we have a whole white paper on this. We've delivered a unique architecture that restricts operator access to customer data, and this white paper provides a lot more details than I can go into today. Additionally, the NCC group performed an independent architecture review of the Nitro system recently, and they found there's no mechanism for the cloud service provider employee to log into the underlying host or to access customer content stored on the instance storage or encrypted EBS volumes. Okay, so let's put all this together and look at the picture end to end. For this, I'm going to use a Graviton 4 server. Here, with this server, we could host many VMs or 1 to 2 bare metal instances. The hosts have an independent lifecycle, all managed by one of our Nitro cards. Most people, when they think of a server, they think of the CPU, the host CPU, as the nexus of that server. But in our systems, it's totally flipped. The Nitro cards are the nexus of our system. They control when the host CPUs boot, after they measure all the firmware and make sure that we're running what we expect. And that could be a metal instance or a virtual instance. Graviton 2 was the first instance in EC2 to encrypt DRAM. And as we've rolled out with Graviton 4, we've expanded that encryption to other interfaces. The interface between our Graviton 4 CPUs and our Nitro cards is also now encrypted. And between multiple sockets of Graviton 4 that are coherent, that's additionally encrypted as well. So if we put this all together, on the left we've got the EC2 control plane. If you call start instances or run instances, that's what you're going to talk to. And there are a number of services there. They're going to do things like authenticate your request, identify a pool of capacity that meets your request, size, availability zone, placement group, and then eventually identify a server that's going to host your instance. And here on the right side, we've got our Nitro cards, our Nitro controllers, and in this case, we're running CHE24XLs, which are 192 gigs of RAM and 96 core VMs. And so when you make that call to the control plane and say, I'd like an instance, what happens? Well, first the control plane sends a message to the Nitro controller saying, please allocate resources for this instance. A message gets sent to the Nitro hypervisor asking it to create a shell of an instance with 96 cores on 192 gigs of RAM. So that's reserved. And then the control plane asks the Nitro cards to please attach the fundamental devices to that instance. So these are things like storage and networking, an ENA device and an EBS volume. And those get attached. Now, they're directly connected to the instance. The Nitro hypervisor is not in the way. We're just talking directly to the Nitro cards here. Next, the control plane says, go ahead and start. And the instance starts, the firmware looks and finds an EBS volume and boots your operating system, and the instance starts running. The picture looks awfully similar for a metal instance. It's actually pretty much the same. Here too, there's the control plane, there's our Nitro cards, and the only difference here is the Nitro hypervisor is missing. And the reason for that is, well, all the functionality for the VPC networking, for EBS, is in the Nitro cards. And so whether or not you're running bare metal or a virtual instance, you have the same instances, you have the same I/O devices, and it looks and feels the same, and you have the same monitoring that you would otherwise have. So much so that we can take those same mechanisms that I mentioned, and we can do things like create Mac Mini instances. So there are lots of developers that want to use a Mac for building and signing software for iOS or iPads or Macs, and want to have the same elasticity and configurability that we do in EC2. And so that's what we did here. We took our Nitro controllers, we put a Thunderbolt to PCIe bridge, connected the Thunderbolt cable to a Mac Mini, and now we have an instance that looks and feels like any other, but is running in your VPC with the benefits of EC2. All right, well, thank you for spending time with me to talk about this. I'll be in the hall to answer any questions because there's no mics to answer questions in this session. And thanks a lot for joining me.